So moving on to the next section here. Standard enthalpies of formation and reaction. So I already kind of talked about these briefly at the very beginning. Okay. We note that both of these are fairly similar. The delta H of reaction and the delta H of formation. Both describe the heat that accompanies a chemical reaction. This one, the delta H reaction, can be generic for any type of chemical reaction. Okay? Just the change in enthalpy that accompanies the chemical reaction. This one, the enthalpy of formation, is very specific to the change in enthalpy that accompanies the formation of 1 mole of a compound from its elements with all substances in their standard state. Okay, so that's very specific. This is the one, the delta H of reaction. That's what we're going to deal with mostly just because of it's generic. We can apply it to any chemical reaction we want. Okay? And so this is how we calculate enthalpy of reaction. Just like we note in a state function here, it's always the final minus the initial. Our delta H of a reaction is always going to be, right, the final state minus the initial state, which is products minus reactants. Okay? So now I expanded this equation, and I know this looks scary, but it's not at all. Okay? So let's walk through this. So that's saying the sum, right, for sigma, okay? This is saying the number of moles of product or the number of moles of reactant. And this is multiplied by the specific delta H of formation of an individual product. So yes, that's right. For delta H of reaction, we have to know the specific delta H of formation and note the standard, right? Meaning at 298. So standard at 298K, okay? So we have to be able to look these values up, okay? So one thing to note, oops, my table was missing a header here, okay? One thing that's important to know, okay, so this is a rule that you've got to know. For all elements in their standard state, so we'll actually just say all things in their standard state, the enthalpy of formation is always 0 because they're already in their standard state. Okay? So you notice here's just a few examples, such as aluminum metal, sodium metal, potassium metal, nitrogen gas, oxygen gas, chlorine gas, hydrogen gas. So because this is at 298K, right, whatever we expect that substance to be at 298K, that is its standard state. And so if it exists in that standard state in a chemical reaction, we can automatically put 0 for its enthalpy of formation. Okay? As it turns out, if something is not in its standard state, we would have to look it up. And so what I want to show you here, I've got a table from the book. This is Appendix 4 from your book. Lots and lots of data. And I'm going to scroll down to table A4.3, thermodynamic properties at 25 degrees C. So that's the same as 298K. So this is standard states. And then check it out. Not only is the molar mass listed, but look, there's that delta H of formation. Okay? Don't worry about this S and this delta G. We'll talk about those in Chem 110. But now if you scan across this middle column here, these are the enthalpies of formation that we could look up for a calculation. Okay? And so if we scan down this list, right, it's a huge, huge list of all of the possible enthalpies of formation we would need. Okay? So that's going to come back in a few minutes when we do a sample calculation. Okay? So we're going to compare these two reactions in the sample calculation. There's the thermite reaction, and of course, if we were in the lecture hall, we would be observing the thermite reaction happening live, which is really cool. Sorry, we can't do that. And then we're going to do the same calculation for the combustion of octane. Okay. So now what I have, though, I have a YouTube video here of the thermite reaction, and we're going to watch this, and we're going to try our best to pretend we're seeing this live.
Oh, hi. I'd like to do a
Oh,
little
hi.
demonstration for you. It's known as the Thermite reaction. And the Thermite reaction is a mixture of two solids, aluminum powder, and this is the stuff that aluminum cans are made out of. But aluminum cans have all kinds of dyes to go ahead and put a label on there and wax on the inside. And this is pure aluminum that's been ground up into the powder form. And this is iron oxide. Fe2O3 is the compound formula, and that's known as rust. And here in Oregon we have quite a bit of rust. So I mixed up these two solids and I put them inside this little porous cup. This porous cup is purchased at a nursery, because nursery people put soil and little seedlings and samplings and things inside there, put it in the ground and let it grow. Well, I've got the solid inside here and a little 4th of July sparkler. And the 4th of July sparkler will throw some sparks down in the mix, give it the activation energy to go. This is an extremely exothermic reaction, so heat will be given off. Our products are going to be iron, solid, and some aluminum oxide. This temperature that we reach is going to be hot enough to melt the iron product that we go ahead and make. So let me get this started. I'm going to light a little Bunsen burner here and light the sparkler. So at the beginning you'll know that it's just sparks.
I love that he uses a Bunsen burner to light a sparkler.
More than just the sparks.
So this is just the sparkler happening right here. Okay, there's the thermite reaction.
That's molten iron that's dripping out of the bottom there. That's liquid iron.
So I'm going to pause that for a minute. That is awesome. There is so much heat released in this reaction. It's so exothermic that it makes the iron go molten. It melts the iron, which is several thousand degrees. Okay, so you can see from my balanced chemical equation, right? Iron's solid as a product, but remember, this is all about the initial state and the final state. So if we wait long enough, that iron will solidify. It will eventually cool down and solidify. However, during the mechanism, during the steps of this reaction, there is so much heat evolved. It liquefies the iron.
The cat food can underneath it is just for effect, because the iron just ripped right through that aluminum can and it's kind of on fire.
So there's a drop of liquid iron.
It's catching the iron so that it doesn't go into water or hit the table or something like that, because it's at about 3250 centigrade. It's very, very, very
3,250 Celsius. Pretty cool. So we do that live in the lecture hall when we can, obviously when there's not a pandemic going on. So in any event, and there's lots of cool videos out there on the internet of the thermite reaction. The Mythbusters a while back melted down an entire car with a thermite reaction. And also, little did you know, this is some of the starting mixture in the solid rocket booster on the space shuttle. Okay? So they actually use this to activate the solid rocket booster, which is really cool. And then it sends a ship up to space.